ME204, Equation of Motion for Rigid Bodies Rotating About a Fixed Axis. Newton's second law of motion states that when objects are translating, unbalanced forces cause masses to accelerate. When we have rotating objects, a moment causes an angular acceleration. However, what do we place here? This is where we place our mass moment of inertia, or the second moment of the mass. So a moment is equal to the mass moment of inertia times the angular acceleration for rotating objects. Let's talk about rigid body kinetics. Before, when we talked about particle kinetics, we look at a small point. In this case, all of the forces act through the same point, so there's no rotation involved. However, when we start dealing with rigid bodies, we now have to be concerned about shape and size. In this case, our forces may act at many different places on the body. Our weight would act at the center of mass. We may have a rotation somewhere on the body, but our forces that are applied to that object can be anywhere on the body. For rigid body kinetics, when we're dealing with translation, we treat it the same as we do for particle motion, except for some of the forces might be offset from the center of mass, allowing for calculation of moments. So we use the sum of the forces equals mass times acceleration, but we might also use the sum of the moments equals the kinetic moments, which is equal to the sum of the mass times acceleration times a moment arm, d, but there's no rotation involved in this case. If we have pure rotation, an object can rotate about the center of mass or another offset fixed point. In this case, for pure rotation, the sum of the forces are equal to 0, and the sum of the moments about the center of gravity is equal to the mass moment of inertia about the center of gravity times the angular acceleration, or the sum of the moments about an offset point is equal to the mass moment of inertia about the offset point times the angular acceleration. For general plane motion, the object both rotates and translates. In this case, we have the sum of the forces equals the mass times the acceleration in all the directions, or the sum of the moments about the center of gravity is equal to the mass moment of inertia about the center of gravity times the angular acceleration, plus the sum of the kinetic moments, which is equal to the mass moment of inertia about the center of gravity times the angular acceleration, plus the sum of the mass times acceleration times its moment arm, d. Let's look at how we solve these kinds of problems. Here we've got a pulley that's pinned at the middle, has a radius of r, and it has a rope wrapped around it with a force F applied. The first step that we want to do is similar to what we did for particle kinetics. We're going to draw a free body diagram with the forces located at the appropriate points. Weight is always applied at the center of mass, and the other forces are located at the point of application. So in this case, our free body diagram looks something like this, where we have a weight, a reaction at the pin in the x and y direction, and a force where the rope is attached to the pulley. Our next step is to draw the kinetic diagram with motion located at or about the center of mass. In this case, all we have is pure rotation. The object isn't translating at all, it's just rotating about a fixed point. If it's rotating about a fixed axis which is not the center of mass, the mass moment of inertia can be shifted using the parallel axis theorem to the point of rotation. But in this case, we are rotating about the center of mass, so our kinetic diagram looks like this, with our mass moment of inertia times our angular acceleration. Third, we write the equation of motion for translation. Sum of the forces in the x direction equals mass times the acceleration in the x direction, and the sum of the forces in the y direction equals the mass times the acceleration in the y direction. So in this case, F minus the reaction in the x direction equals 0, and the reaction in the y direction minus the weight is also equal to 0. Note that the object is not translating, so there's no mass times acceleration on the right side of the equation. Fourth, we calculate the mass moment of inertia and write the equations of motion for rotation. Moments can be taken about any point. In this case, we want to take it about the center of mass. The sum of the moments about the center of mass is equal to the mass moment of inertia about the center of mass times the angular acceleration. So we have an equation, m sub g is equal to I sub g times alpha. We can write the moment as a force times the distance. From our free body diagram, we have a force, F, that's perpendicular to our point of rotation with a distance of r. So our force, F, times the perpendicular distance r is equal to Ig alpha. If it were rotating about another offset point, then we could sum the moments about that point and set it equal to our offset mass moment of inertia times the angular acceleration. But in this case, we don't have that. Here's an example with some numbers. Let's look at one that's in pure rotation. We have a force of 10 pounds applied to the cord attached to the pulley. The pulley has a weight of 20 pounds and a radius of r equals 0.5 feet. The radius of gyration for the pulley is k equals 0.4 feet. We want to determine the angular acceleration of the pulley. Also, what is the tangential acceleration of the rope as it comes off the pulley? We're going to assume in this case that the friction at the pin is negligible. Well, our first step is to draw the free body diagram with the forces located at the appropriate points. In this case, we have a force of 10 pounds, which represents the force applied through the rope, a weight of 20 pounds, a reaction in the y direction, and a reaction in the x direction at the pin. Next, we draw a kinetic diagram with motion located at or about the center of mass. In this case, we have pure rotation, so all we have on our kinetic diagram is our mass moment of inertia about the center of gravity times our angular acceleration. Now we can set these two equal to each other, calculate the mass moment of inertia, and write the equations of motion for rotation, since we're only looking for angular acceleration. Our mass moment of inertia about the center of gravity is equal to mass times the radius of gyration squared, which in this case, the mass is 20 pounds divided by 32.2 feet per second squared, and the radius of gyration is 0.4 feet, and we square that, to get a mass moment of inertia of 0.1 slug feet squared. We'll now apply our moment equation. The sum of the moments about the center of gravity is equal to the mass moment of inertia about the center of gravity times our angular acceleration. Our moment about the center of gravity is simply equal to our 10 pounds times our radius, 0.5 feet. That gives us our moment about the center of gravity. And that's equal to our mass moment of inertia, which we calculated to be 0.1, times our angular acceleration alpha. Now all we have to do is solve for our angular acceleration. Plugging everything in and canceling units, we obtain an angular acceleration of 50 radians per second squared. Now, what about the tangential acceleration of the rope as it comes off the pulley? Well, since we're rotating about a fixed point, we can use that our tangential acceleration is equal to our angular acceleration times the radius, or a equals alpha r. In this case, our tangential acceleration is equal to 50 radians per second squared times our radius of 0.5 feet, which gives us a tangential acceleration of 25 feet per second squared. Here's another example that's similar to the first. However, now we have a 10-pound block attached to the pulley by a cord, and we release the block from rest. The pulley has a weight of 20 pounds and a radius of 0.5 feet, as we had in the past problem, and the radius of gyration for the pulley is k equals 0.4 feet. This problem is a little bit different than the last problem in that our force isn't applied instantaneously and it isn't released instantaneously. We have a mass that is moving. So we have to treat this one a little bit differently. Again, we're going to assume that the friction at the pin is negligible. There are a couple of ways that we can solve this. The first way that we're going to solve that is by separating the problem into different pieces. We have two masses. Each mass has its own acceleration, and so we have to draw our free body and kinetic diagrams that are associated with each mass. So for our free body diagrams, we're going to have the free body diagram of the pulley, which is similar to the free body diagram that we had in the last problem. The only exception is that now we have a tension in the rope that's pulling on the pulley. We're going to represent that with T. We also have a free body diagram for the block, which has a weight of 10 pounds and a tension T. Notice that the tension in the rope is not 10 pounds. If the tension were 10 pounds, then our block would not be accelerating. Next, we'll draw our kinetic diagrams. The kinetic diagram for the pulley is similar to what it was in the previous problem. However, now we have a kinetic diagram for the block, which has a mass times an acceleration going downward. Once we have the free body and kinetic diagrams, we can set them equal to each other, calculate our mass moment of inertia, and use our equations of motion to solve the problem. Our mass moment of inertia for the pulley is the same as it was in the previous problem, which is equal to 0.1 slug feet squared. If we sum the moments about the center of gravity for the pulley, that should equal our mass moment of inertia times our angular acceleration. That moment is equal to the tension in the rope, T, times the perpendicular radius arm, which is 0.5 feet. That equals our mass moment of inertia, 0.1, times our angular acceleration, alpha. Note that in this case we have two unknowns. We're going to need a second equation to be able to solve this problem. To get our second equation, we're going to look at the block. If we sum the forces in the y direction and set that equal to the mass times the acceleration in the y direction, we get that 10 pounds minus the tension is equal to 10 pounds divided by 32.2 feet per second squared to get our mass, times our tangential acceleration. Note that I chose the direction of the acceleration to be positive. This just helps to keep our signs straight as we move through the problem. In this case, I've introduced a new variable, our tangential acceleration. Now we have a second equation, but we have three unknowns, so we need a third equation. The third equation that we're going to use relates our angular acceleration to our tangential acceleration, or our tangential acceleration is equal to our angular acceleration times the radius, or A equals alpha r. In this case, our radius is 0.5 feet, so our tangential acceleration is equal to alpha times 0.5 feet. Now we have 1, 2, 3 equations with 3 unknowns. If we solve these equations simultaneously, we obtain a solution with a tangential acceleration equal to 14.1 feet per second squared, an angular acceleration of 28.1 radians per second squared, and a tension in the rope of 5.6 pounds. There's another way that we could solve this problem. Instead of breaking the problem into two separate pieces, we can treat the problem as a whole system. In this case, our free body diagram would look something like this. Notice that we're not breaking it into two pieces, so the tension in the rope is internal to the system and is not included on the free body diagram. Our kinetic diagram is also whole, with our mass moment of inertia times the angular acceleration to represent the rotation about the center of gravity of the pulley, and the mass times the acceleration of the block. Both of these accelerations are drawn with respect to the center of gravity for the object that we're interested in. We can set these two equal to each other and solve the problem. Our mass moment of inertia for the pulley hasn't changed. It's equal to 0.1 slug feet squared. If we sum moments about the center of gravity, however, our equation has changed slightly. The sum of the moments about the center of gravity is equal to our mass moment of inertia times our angular acceleration plus the mass of the block times its tangential acceleration times a radius, or a moment arm. This is what we call a kinetic moment. It's simply equal to our mass times acceleration times a perpendicular moment arm from the point of rotation. If we plug in what we know, our moment is equal to 10 pounds times the perpendicular radius arm of 0.5 feet. That is equal to our mass moment of inertia, 0.1 slug feet squared, times our angular acceleration, plus our mass, 10 pounds divided by 32.2 feet per second squared, times the acceleration, times the radius arm of 0.5 feet. We can simplify this slightly to this condition. However, we have one equation with two unknowns. We're going to need a second equation. In this case, we want an equation that relates our tangential acceleration to our angular acceleration. So we use our tangential acceleration is equal to our angular acceleration times the radius, or a equals alpha r, with r being equal to 0.5 feet. With two equations, this being equation number 1 and this being equation number 2, we can solve the system to get our solution. Our tangential acceleration is equal to 14.1 feet per second squared, and our angular acceleration is equal to 28.1 radians per second squared, just like we had in the previous problem. Let's look at one more problem. In this case, we're dealing with something where we have a shifted rotation. We have a 2 kilogram slender rod with a length of 2 meters and it's pinned at O. The supporting block is quickly removed, allowing the rod to drop. We want to determine what the angular acceleration is of the rod as it drops. We start by drawing our free body diagram. In this case, we have a reaction in the y direction and a reaction in the x direction at O, and we have the weight of the rod itself, which is 2 kilograms times 9.81 meters per second squared. We next draw our kinetic diagram, which in this case we have a shifted mass moment of inertia, I about O, times our angular acceleration alpha, and it's shifted 1 meter from our center of gravity. We next need to calculate what our mass moment of inertia is about the point O. We do this by using the parallel axis theorem. So our mass moment of inertia about O is equal to our mass moment of inertia about the center of gravity plus the mass times the distance squared. The mass moment of inertia for a slender rod is equal to 1/12 the mass times the length squared. In this case, our mass is 2 kilograms and our length is 2 meters. So our mass moment of inertia is 1/12 times 2 squared, which equals 0.667 kilograms meters squared. This can now be substituted into our first equation to calculate our mass moment of inertia about the point O, which is equal to 0.667 plus the mass, 2 kilograms, times the distance from the center of gravity to the point of rotation, which is 1 meter, squared. That gives us 2.67 kilograms meters squared. Knowing the mass moment of inertia about point O, we can now write our equation to find what our angular acceleration is. We're going to use a moment equation to calculate what our angular acceleration is. So we sum our moments about the point O. This eliminates the reaction forces from the problem. The sum of the moments about O is equal to our mass moment of inertia about O times our angular acceleration. The sum of the moments about O are simply our 2 kilograms times 9.81 meters per second squared to give us the weight of the bar, times its perpendicular moment arm, which is equal to 1 meter. That is then equal to our mass moment of inertia about O, which is 2.67 kilograms meters squared, times our angular acceleration alpha. The only unknown is alpha, and we solve for that, which gives us an alpha equal to 7.36 radians per second squared. If the reactions at O needed to be found, the kinetic diagram that's shown wouldn't be enough to solve the problem. We would need a kinetic diagram that shows the accelerations at the center of mass. Then the reactions could be solved for. In this case, our kinetic diagram would look something like this, with our mass moment of inertia about the center of gravity times our angular acceleration, plus our mass times acceleration in the tangential direction and our mass times acceleration in the normal direction. Note that all of these are labeled at the center of gravity, or the center of mass. This means that our object is both rotating and translating with respect to the center of mass. Note that both of these kinetic diagrams represent the same thing. If we sum moments about O for both diagrams, for the diagram on the left, we have the sum of the moments about O is equal to mass moment of inertia about O times the angular acceleration. If we sum moments about O for the diagram on the right, we have that the sum of the moments about O is equal to our mass moment of inertia about the center of gravity times our angular acceleration, plus our mass times our tangential acceleration times its moment arm, d. Again, this is a kinetic moment, a mass times acceleration times a perpendicular distance to the point of rotation. We know that our tangential acceleration is equal to our angular acceleration times the distance, or times its radius from the center of rotation. In this case, that distance is d. If we substitute that back into our equation for our tangential acceleration, then we get the sum of the moments about O is equal to our mass moment of inertia about the center of gravity times our angular acceleration plus our mass times the angular acceleration times the distance, which is equal to our mass moment of inertia about the center of gravity times our angular acceleration plus the mass times the distance squared times the angular acceleration. If we pull out the angular acceleration, we get the sum of the moments about O is equal to our mass moment of inertia about the center of gravity plus the mass times the distance squared, all of that times our angular acceleration. However, the mass moment of inertia about point O is equal to the mass moment of inertia about the center of gravity plus the mass times the distance squared. If we substitute that into our equation, we get the sum of the moments about O is equal to the mass moment of inertia about O times our angular acceleration. Note that both of these are the same, showing that both kinetic diagrams represent the same thing. Next time we'll talk about the equation of motion for general plane motion of rigid bodies.